all the way up through the salt bridge to go over there. It might. But normally we'll start with a non-reacting ionic compound in there. It doesn't necessarily have to be what was in that container. So we'll continue to look at this, and we'll see some examples, and it'll become more clear as to what goes in what and how they work. Okay, just some terms now for a couple of slides. You don't have to keep drawing the picture. It's the same picture every time. Electrons are flowing from the zinc into the hydrogen. There is a certain force pushing the electrons through. And that force has to do with how good is zinc at giving off electrons? How good is hydrogen at taking the electrons? That determines how hard the electrons are getting pushed through that wire. And how hard they're getting pushed is dependent on what we call the potential difference. Potential difference, again, the zinc has a certain potential for getting rid of electrons. Hydrogen has a certain potential for accepting electrons. That's the potential difference. So we can change substances, maybe use copper instead of zinc, or iron instead of zinc, and we'll get a different potential difference. Yes, sir.
I know that in this class we're gonna have like an extra credit thing for this the battery lab. So is it gonna be like that lab where we're gonna like have one oxidizing and reducing and then put them in separate beakers and look for flow?
Yep. So you're going to come up with what substance you want to oxidize. You have to bring it in. And what substance you want to reduce. You have to bring that in. And I'll have all the beakers out, every glassware that you want. Porous cups, salt bridges. And I'll have a voltmeter that I'll have available for you to see what voltage you get.
So they both have to be solutions then, right?
Yes.
You know, last time you told us how like Bolino did this experiment and he caused havoc in the class. What did he mix with? Could you say like carbon? Or
He had bleach and hydrochloric acid.
bleach and hydrochloric acid?
Yeah. Bleach is hypochlorite, ClO with a negative, and the chlorine in hypochlorite has a positive 1 oxidation number. That's not a stable oxidation state of chlorine, so it will tend to reduce to chloride. So that's, you know, people will bring in bleach. And 2 times I went over to a station and said, Bolino, don't put the hydrochloric acid in the bleach. Oh no, I won't. Okay. I went over again later in the hour. Bolino, you're not going to put the hydrochloric acid in the bleach, right? No. Next thing I know, Bolino's partner said, Bolino! And you see this yellow gas coming up. Bolino's laughing. He put the hydrochloric acid in the bleach and he made chlorine gas. Everybody's out in the hallway. We can't breathe that stuff. It's toxic.
Oh, so it's just supposed to put in separate beakers, but he just combined.
Yeah, I don't know what he was doing. I don't know. Do you know Bolino?
I mean, I've heard because he was in band. So.
Yeah. Super smart kid. I think he's at Harvard now.
He is, yeah.
But yeah, he was a sophomore when he took the class. He was sophomore. No offense, Rashawn. You're not. I would not consider you sophomore. Good question. All right. I'm using the term potential difference here. Again, the zinc has an oxidation potential. How good is it at oxidizing? Hydrogen has a reduction potential. How good is it at reducing? That potential difference determines the voltage. Now the voltage has a couple of other names. it's known as voltage, or it's known as electromotive force. That was in the book. That's what it's talking about. So it's dependent on what substances are oxidizing and reducing. And of course, I think you saw in the book, the volt is defined as this thing. And this term you probably have never heard of before unless you've had physics. A coulomb. Coulombs are the unit of charge. Like I talk about electrons having a -1 charge, that's actually wrong. The electron has a -1 oxidation number. The charge on an electron is measured in coulombs. It's like 10 to the -19th coulombs for an electron.
No, I remember that.
If you did that in physics, yeah. We'll get more into coulombs too later on. So really, volts measure how hard are the electrons being pushed through the wire. How hard are they being pushed? How badly does zinc want to get rid of the electrons, and how badly does the hydrogen want to take electrons? No, not really. Kind of though. It's the pressure that's being put on the electrons to get pushed through, but we don't really measure it in units of pressure like we're used to. Physically, though, it is kind of what it means, like what pressure are the electrons being pushed through it. Yep. Almost done. And just continuing more terms. Are we good with this slide? So this whole system is an electrochemical cell, also known as a galvanic cell.
Says the opposite is like electrolysis.
Yeah, we'll do electrolysis in this chapter too. Electrolysis. A galvanic cell always needs a spontaneous reaction. It's a spontaneous flow of electrons. When you do electrolysis, you send the electrons in the non-spontaneous direction. And where have you heard of electrolysis before?
It says
Was it in the reading assignment?
It just
Oh, I
said
didn't
that
know.
we're gonna talk. It says like you're gonna talk about it in 18.
Okay. So again, that cell potential, that's the voltage. That has to do with the potential for the oxidation plus the potential of the reduction. Added together, that makes up the cell potential, the voltage. Did you catch the symbol the book was using for cell potential? I'm using this like sideways C with the yeah, it looks like a Greek, this is a Greek letter epsilon. The book uses a scripted E.
What's that S?
I don't know, it's like, the book is much nicer than what I can draw. That means cell potential, or oxidation reduction potential. If you don't want to use it, just use the E. Capital E is fine. Most people do that. All right, and then the last slide is this. We can look up what the reduction and oxidation potentials are. There's a table in the book. The baseline reduction would be the reduction of hydrogen ions to hydrogen gas. That has a reduction potential of 0. Some things are better at reducing than hydrogen. Some things are worse at reducing than hydrogen. Hydrogen is just the baseline, the thing that everything else gets compared to. I'll put them on YouTube today. Oh, and notes, yeah, they'll be on Schoology today. Yeah. Sorry that I didn't put them on yesterday. Just one other thing I want to show you, and that is that table on page 825 in the book. That's going to be very close to you for the next couple of weeks. You'll use that table a lot. Okay, we done with the slide? On page 825, which is after 824 had, oh, there's our good friend KSP values. And then we have standard reduction potentials at 25 degrees for many common half reactions. So this just gives reduction potentials. There's two columns of them. There's the first column, there's the second column. They go in order of strength of reducing. The top one here, and I'll just show you what the heading looks like. They'll give you the half reaction and then what the reduction potential is. So you see that little scripted E, that means potential. In volts, the V for volts. So the best thing at reducing is on top. That would be the reduction of fluorine to fluoride ion. So if you're making a battery and you want a high voltage, you want fluorine. Please not bring fluorine into this, one of the banned substances. Hi, Miss Robles.
I didn't mean to bother you, sorry.
That's
Are you guys
okay.
done with those today?
We will be done today, and this BQ wants them tomorrow.
Yeah, we have opposite days.
Oh, great, okay, so she said she's going to come pick them up.
And it's like, why did we never use the holes at the bottom before? Why did we always plug the holes in the bottom?
Yeah, they're already plugged, I just tipped the thing, and I don't know. But yeah, it works very nicely when I plug things on.
Which is what they were designed to do. I always
Yeah,
thought there
yeah.
was a reason we didn't do it.
Yeah, yeah, and no reason.
Okay.
They've always been plugged in. I always just taken them out and, you know, tilted the
Yeah. Well, I thought, like, I knew those were gas collection things, and I thought that there was some reason it didn't work. So
Yeah,
that's
no,
why.
it works beautifully.
So someone just plugged it, and
Yeah.
then everybody was like,
Right.
well, I'll plug it.
Yeah.
Okay, all right. Okay, cool. So you
anyway,
guys are done.
They'll be done, yeah, we'll be done
Okay.
today.
And I
Thanks.
talked to Andy already.
Okay,
Thank you.
okay, yep. So anyway, I'm just going to take you over to the second column, and right in the, about the middle, you'll see the hydrogen reducing, hydrogen ion reducing with 2 electrons to H2. You see it? And the reduction potential is 0.00. That was what I was saying is the baseline. Anything below that, these things are not good at reducing. Like what is my hand close to here? Zinc. Zinc does not tend to reduce to neutral. Zinc is what we consider a reactive metal. It tends to oxidize to Zn plus 2. So if Zn plus 2 is trying to reduce, that's got a negative reduction potential. It doesn't like to do it. Now, if you need something to oxidize, I don't have the next page. I don't just flip the page and find oxidation potentials. This is the reduction potential, but all you have to do is turn the reaction around, and you need one of these products of the reduction. They'll be oxidizing if you turn it around. They'll be giving off electrons. So when you turn one of these around, you just take the sign on the potential and change it. So this, I know the story is only partly told right now. I'm just going to stop there. I want you to not do any homework tonight. Finally, you can take my advice.
Thank you.
No homework tonight. Please don't do any.
Well, you might have that'd be the best day.
And then, of course, we'll, very light, I think we'll probably have a snow day tomorrow. Unless, like, it looks like it's not probably snowing at all. If it just decides to stop, That old one UV van tomorrow morning.
Everybody pour water on the streets.